Now let's take one more example in the Pass1 and Pass2, which combines Pass1 and Pass2 of the assembler. And we'll take one assembly code which I have written it here, and what will be the intermediate code for that, and what will be the machine code for that, and what would be the appropriate data structure for that. So because of I mean space concern, I put up everything in this one sheet. I hope you'll be able to understand it. Right. So this is the assembly code. So start 100. So it will be the first location from where your location counter will be pointing to or will be set to, and then all the instructions will follow after that. Right. So read end 100 and move r b equal to 1. So that is first literal. So what will happen is, see here, when we see read n is the symbol table entry, right? So symbol table at index 0. So that is how it is going to be there. Then b equal to 1, which is going to be literal 0. Right, so first literal which is encountered, so literal 0 entry is done here. This value is entered here. The value of n is yet not known, so location counter initially will not be 109, it will be dash only. Here also it will be dash. This will be filled up only when LTORG is there, and this will be filled up when these actual declarative statements are there. Right, so n equal to 1, both entries are done inside these data structures. There is symbol table in the literal table. Right, and then there is move m, b, and term variable. So term variable is encountered for the first time. So this will be entered inside the symbol table with index 1. So first 0th index is n, second index, first index is term variable. So that is again done. But term is also not going to get initialized with this address, because this will only be available when this value is actually known to this. The location value of this term variable is available at the declarative statement, right? So till then, this term variable will be having this value uninitialized in the symbol table. Then there is a, if you come down here, so that is why here s equal to 1 was there. Now there is a label here. So label will be immediately entered into the symbol table, and all these statements are of length 1. That's why now this will continue 101, 102, 103. So when we are at 103, A is 103. So this entry will be finished immediately. Understand? As I told earlier also, whenever there is a label entry will be done immediately. But for the variables like n and term, it will take it will wait for the reference to be made available, whether it is forward reference or backward. In this case, it is a forward reference. So it will wait for the actual values to be available of the location counter. Then this was symbol table with index 2. Then imperative statement 03, then B register, that is 02, so register 02, and term is referred again. So we are just specifying the index location where it is present. So it is present inside a symbol table with location 1. Right, then there is LTORG. Now before this LTORG, how many literals are there? There is only one literal, that is equal to 1. So only one address would be required. That's why 104 is there. Right, and 105 is not actually given because only one literal is there. That location itself will be utilized, 104. Right, then assembler directive with 05, declarative with 02, and constant with the value 1. So that value was equal to 1. That's why this value is specified here as DC1. Right, then continuing further, 105 is increment, location counter is incremented as per our algorithm, modifying the location counter and read the next instruction. So move R C comma C double equal to 2. So there is a new literal, so new literal entry would be done. What is this is an imperative statement. So imperative statement with 04 code, C is register 3 and number 2. So literal with index 1. Right. So in that way, this intermediate code is ready. Then move M, that is the imperative statement with 05. B is register 2 and equal to 5. So new entry inside the literal table. What is the index of that is? It is index of 2. So that's why L comma 2. Then LTORG. So now see here, when this LTORG is there, so 107 is the location where your first entry of equal to 2 would be there, and 108 is the address where this equal to 5 entry would be there. So that's why I have just skipped it and I am going to write it 108 for this one. Right. So 108 is for double equal to 5. So LTORG is going to make use of these two addresses for the two literals, that is 2 and 5. Okay, so what will happen is assembly directive 05. It was assembly directive 05. So here also it is assembly directive declarative statement 0202. That will remain as it is, and the actual value of the literal, that is called C comma 2 and C comma 5. Right. So that is how it is done. Then it is that address 109. After this, what is the next location? Next location counter is 109. So 109 and DS1. So this is the first place where the value is declarative. The address of location counter of n variable is coming up. So what is the location counter? 109. So what will happen here is inside the symbol table will be populating 109, right? And term variable likewise is going to come up at 110. So this will be updated accordingly in the symbol table, right? So this LT over the statements are going to populate here for 104 and then 107, 108 in this way. And at the same time, the pool table. So how many times this LT over the statements are there? There are 2 times LT over the statements which are coming. So LT over G1 is saying how many literals I have seen when the LT over the statement was encountered. When LT over G1 was encountered, only 1, right? So that was equal to 1. And how many LT over the statements will be there here? I mean, it will be totally it is 1 more. So it is LT over G. When it is seen second time, it is second and third value which is there. So in that way, it is going to point. Default is 0. It will start from 0 pool table, but when the first entry is done, it is going to then refer to the total number of entries. So this is LT over G for first time and LT over G for the second time. In that way, total cumulative count will be present available inside the pool table. Right. So what is this? Is statement symbol table with index 0, symbol table with index 0, and declarative statement number with 0, 1, because DS and DC. That DS is 0, 1, and that's why no this would be there, and the value of that declarative class is 0, 1. Then value of that is supposed to be specified inside the operand specification for the constant. So value is 1. So C, 1, C, 1. So this is how the data structure and the intermediate code would be ready for the assembly code. Generating the machine code, having available with you all this information, this will be then submitted to the Pass2 of the assembler. So Pass2 is very simple. It is going to generate the machine code, right? So just see here, forget about everything. Wherever you see the numbers, just put up those numbers. So 09 is placed here, 00 is placed here. But whenever there is a symbol from which address it is going to refer to, that address you need to find out. So it is at address 109. So you just populate with the address 109. Whenever such type of statements are there. Likewise 04, then 02, and the index, the address for literal 0. What is the address for literal 0 is 104. So we put up 104 here. Then 05, 02, and S, 1. So 05, 02, and S, 1. What is the address of this S, 1 is 110. So we put up here 110. Likewise, forget about this. See, label will never be put up as part of the machine code. So label will not be there. So directly we will have to start from this 03, 02, and S1. 03, 02 will go as it is, and what is S1 is 110. So 110 is put up here. So what I have done is label, any label will not be coming up as part of the machine code. It is already taken care of, right? Then LTORG, this is a special case. Whenever there is LTORG, you have to write here machine code as 00 2 times and the actual value only, right? So this is the thing that you will have to do, because literals anyway are entered with the addresses. So it will be taken care of by the system. When it sees 00, it will be it will get the actual value from the pool table, from the literal table, right? and the addresses and the values for that. Then this is 4 and 3 and with literal 1. So 4, 3, and what is literal 1 is 107, right? So the address is 107. So 107 is populated. Likewise 05, 02, literal 2. So 05, 02, literal 2 is present at 108. So 108 will be populated here. Then again LTORG, as I said earlier, LTORG is having a special machine code which is 00 twice. So 0000 and the actual constant value which is going to be there. So constant is 2, which is populated here as 2, which is written as 2, and here it is 5, so it is written as 5. And we don't have the machine code for this type of statements like start. We don't have write the machine code for this, and we don't write the machine code for and declarative statement with the 1 and term. These are all actual storage spaces which are going to be there, right? So generating the machine code is pretty much simple and it's easy. So Pass2 as such is not that difficult to understand. And only thing that you have to take care is that in case of labels, if it is there, labels will not have the machine code. I mean, label will be skipped, and as far as LTORG statements are there, you have to make sure that it is 0000 and followed by the value of the constant which is there. Okay, so I think this is done. So now next thing that we need to see is what type of referencing could be possible here, right? So in this, we are referring to a variable which is not present as of now immediately available to the system, right? So it is somewhere defined later, but before that, no, we are using it. So this type of referencing is known as forward referencing, and this is basically a problem, no, inside the assembly. That's why, no, I mean, in the two pass translations, no, we can handle forward references easily, but in single pass, it is very difficult to do that. So that's why, no, that there are two passes which we are having inside the assembler, right? So likewise, no, there could be a possibility of backward reference, like something like I'm saying start 100, and okay, what I will do is I will take one example and I will explain you so that it becomes easy for you. So what is forward reference and what is backward reference? This is an example of forward reference, right? So we'll take up a small example and then we'll explain you for that. Okay. And that is the last topic, and the solution for that is again handled by the word known as backpatching mechanism. So we'll look into that backpatching mechanism with a small example. Okay. Okay, so what is forward reference problem and what is backward reference problem? So backward reference, I will backward reference and forward reference, right? So what is backward reference is, let's say start 100, okay, and I'm saying X DC with 1, okay, and there are some statements here, and then I'm saying move R, let's say areg, and I'm saying X. So I'm going to refer to a variable which is defined earlier, right? Defined earlier. So this is backward reference. And the reverse of this is, no, when I swap this, it becomes a forward reference. So what is forward reference? Forward reference example we have already seen, right? So let's say start 100, just duplicate, I mean, replace these two things. No, it will be easy. So move R, areg X. So I'm just using it X variable before it is actually encountered, or maybe the variable is declared, right? Let's say this is the value which is there. So this is an example of forward reference and backward reference. So how these problems could be handled is, let's say I'm giving you one example for that. Let's say there is something like start 100, right? Start 100. And what will be the location counter for this? So just we will see that, and we'll also generate the machine code for that. We'll have a number of things here, but we'll skip certain things here so that it becomes easy. So let's say move R areg, and I'm saying the variable is X, and that location counter for this is, let's say it is 100. Okay, and so what will happen is, okay, first of all, note down the small code so that it becomes easy. Breg and Y, right? So I'm giving this as 101. Then I'm saying subtract instruction, which is saying areg something, right? Areg and Z. So there are three variables which I encountered, and there are some things which are there. So maybe 103, 104, 105, and so on. And 106 somewhere, no, I'm saying that X is declared with value 5, then Y is declared somewhere with the constant value of 1, and Z is somewhere coming up with DC as 2, right? So the values are present here, and it is at 106, 107, and 108. And then there is something like end statement which is there. Okay, so if this is the case, right, then what will be the machine code for this, right? So, and how it is handled. So I hope this is now the concept is known to you. What is the example here? This is the example of forward referencing, right? And forward referencing problem could be handled by a concept known as backpatching. So how this backpatching is going to be done, and this is nothing but the incomplete instructions, right? So these are the instructions which are going to be incomplete. So where to record all these incomplete instruction? So table of incomplete instruction is also known as TII. Table of incomplete instruction is known as TII. So there would be a backpatching list which will be created. Backpatch list, or table of incomplete instruction, TII. Right. So what will be there inside this is instruction, address, and the symbol. Right. So what are the instruction addresses and what are the symbols? these are the entries which are nothing but the address of incomplete instructions, right? So address X, the first time now when we generate the machine code for this will be what? It will be like 04, then the register array, so that is 01 and dash. Keep it dash as it is as of now, so that we don't know at which place it is going to be there. We will only come to know when it is actually declared, and then the entry inside the symbol table will be updated, right? So what about this is 01, then that is 2 and dash, right? Likewise, what a subtract instruction is 02, then array is 1 and dash. This is the places where X, these are the places where X, Y, and Z is there, and these are the incomplete instructions, right? So what we will do is symbol X is at which location counter, so this is 100, then Y is also encountered, which is at location 101, and Z is also encountered at location 102. So these are the instructions which are still incomplete, and we need to process this. So these entries, which we have done inside this, is known as the backpatch list. So forward referencing problem could be handled by the backpatch list. So what is the meaning of this? That when it will be processed. So when X is seen by the system, it is at which address? So X is seen at the address 106, right? So X is seen at the address 106. And that's why what is the meaning of this is this 106 has to come down here. So 106 will be placed here. Likewise, this is going to be available at 107, right? So 107 will be entered here, and then 108 will be replaced here. So this is incomplete instruction which for which the processing will be done. We are least bother about what is there after this. So this concept actually is known as the backpatching concept, and it is basically responsible to handle the forward referencing. So it's like pointer to the actual addresses, right? And there is a list of instructions which are incomplete instructions, and that we need to process, right? So what we have seen is in the two-pass translation, it can handle forward references very easily. That is what we can say. And in the case of single pass translation, the LC processing and construction of symbol table proceeds in the two-pass translation, but the problem for forward references is tackled using a process called backpatching. In single pass translation also, this could be useful to us by using the backpatching concept, right? So can handle a two-pass assembler can handle the forward referencing very easily. Likewise, if just to summarize everything, LC processing is performed in the first pass, and symbols defined in the program are entered into the symbol table, right? And second pass, what we do is we synthesize the target form, and we using the address information found in the symbol table, right? And so the first pass constructs the intermediate representation for use by the second pass, and this representation consists of mainly two main components. The one is data structures, and like example is a symbol table, then your literal table, and so on, and a processed form of the source program, which we call it as intermediate code. So this is how it's going to handle when the two pass translation is done. Whereas in the case of single pass translation, what could be there is there will be the usage of backpatching concept, which is very heavily used, right? So LC processing, as we have seen, and construction of symbol table proceed as in the two pass translation. But the problem of forward references is tackled using a process called as backpatching, right? And operand field of an instruction containing forward reference is left blank initially, and that is what I have told you, that 106, 107, 108 will be left blank initially, and the address of forward reference symbol is put into this field when this definition is encountered, right? So when it is encountered, we are putting up those values into the blank entries. So the operand's address is later indicated by adding an entry to the table of incomplete instruction, that is an instruction address and the symbol, and that's what this is we're talking of. And by the time the end statement is processed, the symbol table would contain the addresses of all the symbols defined in the source program, and a table of incomplete instruction would contain information describing all forward references. So almost everything related to the various phases of the assembler we have seen. However, what we have taken care of while designing the two-pass assembler if I want to summarize it, task performed by the first pass is something like separate the symbols. We will be separating the mnemonics. We will be generating the opcode and the operand fields in this task, pass 1. Then what we'll do is we'll build up all the data structures like symbol table, and then we also perform the literal processing, so LC processing, not literal, but then location counter processing, and even construct the intermediate code representation for that, intermediate representation for that. That is the work done by the first pass of the compiler. And the second pass is pretty simple, and what we do is just the synthesis. We synthesize the target program. So we generate the machine code from the available intermediate code and the data structures from pass 1. So I hope you enjoyed this listening of pass 1 and pass 2 of the assemblers with examples. Similar sort of examples you should practice by taking some of the help from the examples available in the internet also, and I've shared you some of the examples to practice. Please go through those of my videos a couple of times so that now you understand it very clearly. Thank you.